In this video, we will be discussing convective heat transfer, and specifically we're going to be looking at Newton's law. And the key thing to take home here is that whenever you see the terms moving fluids in your problem statement, or if you know you will have moving fluids in your example, then we will have convective heat transfer, because convective heat transfer is what allows us to describe how that thermal kinetic energy is exchanged between an object and a fluid that is moving. And so what Newton's law tells us is that Q, which tells us the rate of heat transfer, in other words, how many joules of heat per second are lost to the environment, this is equal to something called H. H describes our heat transfer coefficient, and we're going to be multiplying this by an area. I like to think of this as the exposed area, and we will have temperature at the surface minus some kind of bulk temperature of our fluid of interest. And so to work through an example problem and give some ballpark figures for what these values typically are, if we look at air, we know that air has a value of 25 watts per meter squared per Kelvin for its heat transfer coefficient. And let's say I had an open stove top and I wanted to maintain T surface at 100 degrees C, and the temperature of our bulk fluid was 15 degrees C. And so my question is, how much heat is being lost to our environment that I need to supply onto this surface such that I maintain its temperature of 100 degrees C? And I will say that we have an area of 10 square meters, which is a pretty big stovetop, but people like to eat. So with this, please try to see if you can solve this problem, and we're going to work through it. And so it is really just a matter of plugging and chugging. What we have is a value of 25 watts per meter squared per Kelvin. We're going to be multiplying this by our exposed area, which was 10 square meters. And we also have a temperature difference between our surface and our bulk fluid of 85 degrees C. And this came from 100 minus 15 degrees C. Also make a note of how when you're dealing with temperature differences, a delta Kelvin is equivalent to a delta Celsius, because even though you need to add 273 to your Kelvin to get degrees to your degrees Celsius to get degrees K, they do have the same 1 degrees C is the same as 1 degrees Kelvin. I hope I'm describing that right, but you get the gist of it. The point is, doing a dimensional analysis here and actually plugging in and multiplying these values, what we see is that we have square meters canceling out, and we have degrees Kelvin canceling with our difference in degrees Celsius. And what we find ultimately is that we have 21.3 kilojoules per second of energy being lost due to convective heat transfer in this given situation. And so if we had a little flame underneath here, just terrible flame, but if we had some kind of heating element, let's say a copper coil, we would need to be providing 21.3 kilojoules per second, aka 21.3 kilowatts, into our system in order to maintain this constant surface temperature. So that's going to be it for this video on an intro to convective heat transfer. I hope you guys find it useful, and thanks for watching.